I think it's recording. All right, let's just see if it records. How are we doing, everybody? Doing good, everybody? Okay, so someone wanted the Twitch stream, so should I check on who's my Twitch guys? Nah. I'll wait for that surprise later. Anyways, I wanted to do an active lab for today, and the reason why I decided to do an active lab is, well, because I value you guys' education, and I want to show you guys what I do for if I were to be a 320 professor, because they're telling me I can't, but I'm like, let me prove it to you guys. So, frequency response. You guys remember what a frequency response is, right? Actually, do you guys know this, what this is right here? If I have t time, right? Is that good with everybody? And then, I don't know, I have some type of, what do you call it? Sine wave like this, correct? And it's, let's put the 1 millisecond period. What's the frequency? Do you know why I use 1 milli, 1 kilo, 1 giga, 1 nano? Because it's easy. It's easy things to remember, okay? So if there's one thing everyone can take home, use 1 millisecond, okay? Or 1 kilohertz or 100 nano or something like that. They're really easy numbers. You can just create problems on the fly. Milliamp, 1 volt, 1 kilo ohm, right? Because I don't want to throw numbers at you guys. I want to teach, okay? Does that make sense? Why I do things the way I do? Anyways, so I have a frequency, right? And let's just say it's at 1 volt. Is that good? Everyone understood this? So what if I create the following? If I create another, what do you call it? Let me see. Here's a signal in time, right? It's just existing as a signal wave, right? Signal system, guys. You guys understand what's going on, right? Let me see. I'm gonna give someone PTSD. Exity. Yeah, you guys don't like that, huh? 1 volt, right? E to the, what do you call it? J, what do you call it? Positive J 1K. Actually, no. 2 pi 1K, right? Minus, what do you call it? E to the minus J 2 pi 1K, right? All over 2J. Is that a sine wave? Signals and systems. Really cool, because all signals and systems are just amplitudes and Euler's equations. Right? Everyone understood what's going on? Not too hard, not too bad. Anyways, I hope my... should I... Twitch. This is going to be so funny. Let's see if there's any complaints. New from Luna. How do I check my, what do you call it?
Comments or chat?
Yeah, chat. Creator Nana stream. Let's see what happened. I have PTSD. Stop with the math. Go to Battlefield 6. This guy is pretty smart. He should be a teacher. You guys are funny. Anyways, no, the reason why I haven't streamed in a while is actually I'm doing home renovations. Okay, side chant. I'm actually building a super gamer cave right now. I had one, but then I did some crazy renovations in my house, and now I'm making. I just got a big, like, super heavy duty, like, arm, because I have this ultra wide monitor. It's like, I think it's like 42 inches, but it's like huge. It's like, I think as big as half as. Yeah, it's huge, curved, OLED. 144 hertz or something like that. Actually, speaking of 144 hertz, okay, I see. I'm trying to connect everything. What if I do the following? I'm doing the math in my head. 144 hertz is 1K divided by 1 point something. Oh, upside down. Let's say I have a frequency right here. Actually, okay. Remember that 1 kilohertz signal, right? If I do this right here, F, right? There we go. And I have my voltage right here. Does that make sense? What am I going to see in terms of frequencies for just that one sine wave that we had right here? What are we going to see? Does that make sense? one-sided Fourier transform. If I wanted to do a double-sided Fourier transform, it would be like this. This is 1 volt. This is a 1.4, 1/2 volt right there. This is minus 1k and plus 1k hertz, right? Does that make sense? The double-sided Fourier transform or the two-sided Fourier transform, right? But if you wanted a single-sided one, like how we do it in real life, spectrometers, audio spectrometers, you just flip it and then everything kind of multiplies like that. Everyone understood that? Easy stuff. So let's just say I introduce another signals and systems. I hate signals. It's okay. Right? I have some random signal. Like this. Yeah, whatever. And I'm just going to do 0.1 millisecond period. Right? What frequency did I go? Or did I choose? If it's 1 millisecond or 0.1 millisecond. 10K? 10K hertz? Wait, 10 kilohertz. Cool? Is that making sense with everybody? So what if I did the following? If I threw this signal and this signal together, actually. Here's our spectrometer, right? If this was, I don't know, 0.1 volt right there, right? What's it going to look like here? Right? Wait, 10 kilohertz. Is that making sense with everybody? Are you guys understanding what's going on? So what if I treated this as like, hey, I want this 1 kilohertz signal, right? But I don't want this guy. It's noise. Think of it as noise. Right? Right? So what if I did the following? You guys know what a mixer circuit is? What do you call it? Series mixing? No? An op-amp? Non-inverting? Inverting? Mixing? Summation circuit? Let me see. Oh, can't draw today, y'all. Plus, minus. Right? You guys remember this from 221, 320? The labs? Not that bad? What am I going to call this one? I'm going to call it 1K. 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 Is that cool with everybody? Cool? And then I'm going to put the, what do you call it, the 1 kilohertz signal there, and then the, what do you call it, 10 kilohertz signal here, right? Or let me just do, like, I don't know, V1 and V2 to make it more easier. And this is V out. Okay? What's the current going into this node? Actually, let's talk about things. What's the voltage here? What's the voltage here? You guys like the confidence boost? Yeah, you wish Dr. Zaya did this? What's the current here? 1 milliamp, right? Because well, we have V1 minus 0 over this 1K resistor, right? I1 is equal to V1 over 1K, right? What's the current here? 1K. Everyone understand the basics and the fundamentals, okay? This is what I would do as a 320 professor, okay? This is why I'm petitioning. I'm gonna show them these videos and be like, hey, and the stream, okay? Maybe I'll be the first. No, I won't be the first because I think there's other institutions that do Twitch streaming too. But I want to be like the Twitch guy or whatever. Anyways, which direction do you want to go? Do you want to go this way or that other way for IF feedback? You want to go left to right or right to left? Left to right? Like that?
Yeah.
What's the current? 0 minus V out over 1K, which is equal to minus V out over 1K. Is this not that hard? It's not that bad. And then we can find what V out is with respect to V in or V1 and V2. Everyone knows how to do a mixing circuit. Series mixing, shunt, outputs. We're sampling this output, right? It's a voltage. The input is the input is a current, right? Current's going in, right? The output is a voltage, right? Everyone understand that? I'm gonna type in something in chat. Let's see. It's my wife. I thought you were skipping work, and then I saw the notice. School Wi-Fi messing up my comments. Also, I just noticed I have no work tomorrow. What? Moi? Okay, let me see. Blush. Series mixing and shunt sampling. See if anyone does this. The doctor, wait. I don't think Dr. Zai went over this because this is a 420 topic. Dr. Baker loves this. He teaches this in his 320 class. I know. This is very important as an analog designer. Voltage sampling, series mixing, current sampling, all this stuff. I won't teach you that, okay? That's way above the level of this class. Mixing, okay? So if you wanted to do something cool with your final projects, I'm going to be announcing that very soon. Tonight I need to publish lab 8 and 9, or what's it called? BJTs and NMOSs and PMOSs, right? Transistors or MOSFETs. I blanked out, right? And then after you guys do your BJTs, I think right then there I'm confident with assigning the final project. But the final project is like, oh, do something cool with like whatever we did in the class, transistors, ICs, all that stuff, okay? So if you wanted to build this and then put like a transistor here, like I'm gonna just draw it. Like here's your NMOS, and build an amplifier right there. Because this right here amplifies the voltage, right? But this right here, if I put a resistor here, like I don't know, 100 ohms, right? It's gonna kill the output. Can you agree with that, right? So we need to drive that with a current driver, right? I'm not gonna teach this right now, but that's for lab 9. We're gonna build current drivers. Actually, BJTs, you can build one too. It's better. Anyways, I'm going on a tangent. Frequency response, okay? Everyone understand what's going on? So I want to get rid of this thing right here, right? So how am I gonna get rid of it? With a filter. Right? Filter. Low pass filter. Right? Signals and systems. Scary. Page 2. So, you guys remember how to do Bode plots? No? Yes? No? Who doesn't? Don't be afraid. It's okay. Don't worry. I'm here to give you guys your education. But before that, signals and systems. Time to teach signals and systems. Who didn't come to my lecture last night? Do you guys remember, what do you call it? I'm going to draw a scary circuit. Ooh, scary, right? Pretty cool, right? RC. Make sense? Let me see. Do I want to solve it like that? Anyways. Here's my V in, here's my V out. I'm thinking about how I want to show you guys this without making it too complicated. What's the current in a circuit? What's the current? Say it. Not hard, right? What's the other answer? Come on, y'all. I'm scared. Trivial questions, right? I'm not the king of trivial questions. That's Dr. Baker. I'm the king of copy paste. That's what I'm calling myself because I'm not lazy. I just, work efficiently. Okay, that's what I'm saying now. But copy paste, okay. Anyways, because if you guys notice my lab manuals, I just copy paste the same circuit in a way because I want to teach you guys the fundamentals, right? It's easier to teach you the fundamentals when the numbers are easy, okay? Anyways, no hard numbers, okay? And then you have to do, okay, I'm not going to solve this, but point is you're going to see like, oh, V out, you have to do like the, what do you call it, the auxiliary equations, right? Do you want, I'm going to scare you guys. Do I want to scare you guys? I don't think I want to. Should I scare you guys? Yeah. Because I'm actually blanking out too. V in, V out. Y prime minus what's it called? RC Y is equal to, I think this might be the answer. I don't know. X. Remember these equations, right? When we were doing signals and systems? What was it? Computer assignment 4, right? And you have to find this transfer function. Pain, lots of pain. I know. I don't like it either. So I don't want to solve it like this. I'm going to put a question mark here. Okay. You guys remember your 221? Impedances. What's the impedance of R? Just R, right? What's the impedance of a capacitor?
Negative J over JC.
What do you call it? 1 over J. Wait, no. SC, right? Right? Are you guys remembering this stuff? What's S? Omega or no, sigma plus J omega. Right? You guys remember this? Signals and systems? 360? Dr. Steve, Dr. Morris. I'm throwing you guys. I'm throwing you like subliminal messages. Boom, boom, boom. Not that hard, right? What's S also equal to? Oh, wait. Hold on, sorry. What's omega equal to? Right? 2 pi f? Right? So, why did I have this sigma right here? Because you can just throw a pulse into this thing and you can see the pulse, boom, right? Decaying circuit, right? And what is this omega here? The sine wave. Signals and systems and electronics having a baby right now. It's fun when you start understanding what's going on, okay? That's why I want to teach 320, because I think I have a beautiful dance between the 360 students and the, 320 students, but I can inject this stuff. It's all useful things, okay? Anyways, let's stop talking. V out, S, V in, S. What's the transfer function? Or actually, let's start simple. What's V out using a voltage divider? The impedance right here.
R plus 1 over SC.
Thank you. I actually enjoy the comments. You know what? Let's just see what our Twitch chats are crying. Bots? Can we get a mod check in chat? The heck? OBS would never allow bots. Who's giving me these ones? You guys are funny. Anyways. How do I solve this? So you guys remember? Okay, because remember that one assignment? I think it was the op amps or something, where I told you signals and systems. We have this little trick. You see this guy right here? It's scary, right? But if I just think of it like N and D, right? Numerator and denominator, right? And this right here is N and D, right? Right? How do I get rid of the D? Multiply everything by D over D. So now this goes away. So it's Vn times 1 over, then the D gets multiple. It's SC is equal to D, correct? So it's going to be SRC, right? Right? So now I'm thinking about this differently. You guys like that trick? Magic. Cool. And that's it. Yeah, that's it. That's the answer. Was that a very not surprising? Actually, better yet, let's do it something differently. Remember how S is equal to, well, I'm just going to make it simple for you guys. J 2 pi f, right? J omega 2 pi f, right? Vn times 1 over 1 plus J 2 pi f RC. Is this looking familiar to everybody? And then let me see. I'm going to do one more thing. So now instead of it being in terms of S right here, right, I made it in terms of F, right? Because I got rid of all the S's. The out, F, the out, S, right? I just did a change in variable, right? So you see that this is my play variable right there, right? So that's a function that's based off these dudes, right? But I'm going to do something with, what do you call it? This guy and this guy right there. We're actually on these two guys. Okay? On the next page. Page 3. Chat, how we doing? See, now it makes sense for me to say chat. Not ChatGPT. I hate ChatGPT. Okay. So I'm going to do the following. V out of F is equal to V in F times 1 over, I'm going to scare everybody, 1 plus F over F3 dB. I think I should put the J in here. There we go. Where F3 dB is equal to 1 over 2 pi RC. Is this clicking in anyone's minds? Who's actually watching the old Dr. Baker videos from 220? Yeah, he taught this in 220. And I'm teaching this in 320. It's okay. Don't worry. Don't worry. He's not here anymore. I miss him a lot too. Anyways, is this making a lot more sense, everybody? So, yeah, I'll inject signals in systems. Remember that funny problem I was trying to show you guys? Let me do it right here. RC, can you see that color? Y plus, yeah, is equal to X of T. Right? Do a Laplace transform, right? Right? Cool? Next step right there, right? Right? Transfer function. Remember that? Easy stuff? What's the answer? Bingo! Am I giving you guys your education's worth? Yes? Easy stuff? You wish Dr. Zai was doing this? You wish he actually just picked up a marker? Anyways, so what happens when F goes to infinity? Or actually, okay, better yet. So let me do the magnitude response. You guys remember, not magnitude, absolute value or magnitude, absolute magnitudes, right? So V out over V in, magnitude, right? Remember that? What's the magnitude of 1? Thank you. What's the magnitude of this guy? Square root of 1 squared, right? Plus F over F3dB squared. Right? Everyone understanding what's going on? Now it's all, there's no imaginary numbers. It's all real. Okay? So, what if F goes to infinity? If F goes to infinity.
0.
Right? So what does that mean? The magnitude goes to 0, right? Everyone understanding? What if F goes to 0? DC. Easy, right? Now here's the other question. What if F is equal to F3 dB? 707, which is LOL backward or upside down. Any questions about that? Has anyone heard about 707 in their lectures? No? Or yes? A few no's, a few yeses? This is something Dr. Baker taught like day one, or not day one, but like first lecture of Bode Plots. This is why he taught them. Anyways, 707, 3dB. What's another number everyone thinks about? Pi over 4, 1K, 1 milli, all these funny numbers. 3.14. These are all important numbers to know, okay? So, I was going to make you guys do a frequency response lab, and you're going to have to manually, turn the frequency, but that's painful, and it will take like an hour to do the lab. I don't want to do that. So there's this beautiful tool that was invented by a guy named Bode, I think. He created this thing called Bode Plots. Right? You guys know what Bode Plots are? Right? It's just an easy way to draw stuff, okay? It makes it like, it's what do you call it? This tool can actually do it, kind of. It does a more accurate representations of frequency response thing, so I'll show you guys an experiment at the end of this class, okay? Anyways, before I show you guys Bode Plots, I need to show you guys signals and systems. Remember this imaginary S, real S, right? Signals and systems, right? And if I have a pole right here, right? What's the region of convergence? Right there, right? Easy stuff. It's stable. It's a right-sided function, stable, because it includes the imaginary axis. It's clicking, right? But what's this going to look like? It's going to look like, well, it's going to be like this decaying thing, right? Easy. But we're dealing with things that are what do you call it? Squiggly lines, right? Sinusoids. So what am I going to do? Pole right there, right? What happens when I put a pole there? I have to put the complex conjugate. I like the head nods. I like that, okay? What am I going to do right here? 1 kilohertz. Right? So that if I flipped it like this, right? Minus 1 kilohertz. Right? And if I zoomed it in like this, right? You see that? Or actually, no. If I bent it like this right here, like, you see how I'm bending that paper? It kind of starts looking like, oh, you guys are getting your education's worth. Like this. Yeah, actually, this is great. See the poles? The poles are going up like that. That's what's happening. Remember that Laplace transform we were doing, and you see these poles going up? That's these guys. Poles. Getting your money's worth now? Now here's a good question, and this is actually a research question. What's the region of convergence? Well, it goes like this, right? Right? It goes the other way, right? Is it stable? It's like on the it's like critically or something like that. I don't know how to explain it, but it's oscillating. So it's not necessarily going to, it's not exploding, but it's not decaying. Okay? Well, if you think about it, the function generators here are stable. It's just that the function generator always like adds juice. Like think of like an engine. So if the engine was like an infinite source, of course that's not stable. It doesn't exist. But it's decaying a little bit, but it's always adding a little gas to like keep that sine wave from spinning around, okay? So ideally, yeah, it's unstable, okay? But it's oscillating, okay? It's a sine wave. Make sense? So if I were to do the following for poles, I want everyone to learn this, okay? All poles, here's frequency, okay? F. So what does this mean with this axis right here? This right here is that F axis. Is everyone understanding what's going on? Fourier is within Laplace. Yeah, it's cool stuff. Anyways, which means you can get the Z transform from this too. Cool stuff. Anyways, poles. Poles look like things that go up, right? They go up into space, right? You guys remember the Laplace transform tool I gave you guys? Poles go up, assignments due tomorrow, right? Yeah, Laplace transforms. So things got to look like a pole. Let me remember. But poles, let me see. Poles, give me a second, because this is why I brain farted the last class, so my Monday labs are like, whatever. But, can everyone agree with me? There it is. Can everyone agree with me that if, let me see, if this value somehow became -1, right? Yes?
So for the Fourier series and the Laplace transform, I thought that a Fourier series only exists if a signal is stable, but if the poles are on the imaginary axis, they can't be stable.
So Fourier series, they have to be stable, because Fourier series is like a series. It's like A plus B plus C plus D plus, well, what did he call it? Morris called it like the A's and the B's or whatever. Sounds like the birds and the bees. Anyways. But anyways, those are always stable because you're using a resonant function or a resonant frequency, or not fundamental frequency, okay? But I'm talking about Fourier transforms, which can be aperiodic, periodic, and then you have the digital versions, digital, aperiodic, and periodic. So, okay, I'm going to say it. Fourier transform, Fourier series, discrete Fourier transform, discrete time Fourier transform. And then there's other things, but anyways. That's a 480 problem. Wait next year. Okay, back to what I'm saying. Let's just say this for some reason turns to -1. Or, let me see. Where's my 1 over s? 1 plus SRC, right? For some reason, this goes to, like, this denominator goes to 0, right? What does that look like? A pole, right? But you know the magnitude response, right? If this goes to infinity, it goes to 0, right? This is where it starts making, it doesn't make sense, okay? I brain farted in Monday, but I'm not going to do that mistake again. So this is how Papa Dave remembers it. Poles, if it's 1K, right? 1 kilohertz pole. At that point, go down. Okay? Everyone understood? Poles go down. And you want to know what I'm going to do? I'm going to do a mountain analogy. If you know mountains, right? They got the snow on the top. It looks like a pole, right? So if I just tilt it like that, okay? Poles do that. Here's 10 kilohertz. And this right here is 0.1 kilohertz. Is that cool with everybody? If I were to do the following, okay? The value right here, actually this slope right here, you're going to memorize this. Decade. It's minus 20 dB per decade. Okay? From the pole all the way to infinity frequency. Everyone going to memorize this? Okay? Because I don't think you're going to ever use this again in the courses, except if you take my 420 lab. But I want you guys to know this, okay? So, what's up? Okay, this is a 20 log dB, right? 20 log whatever, 20 log, right? This right here is 0 dB, right there, right? So if I go 1 decade here and it's a minus 20 per decade, what's the value here? Right? Everyone understanding what's going on? If I go to 100K, right? What's the value over here? Everyone understanding what's going on? I'm going to write on another piece of paper because I think this is very important. Page 1, 2, 3, page 1, page 2, page 3, page 4, page 5. Okay. Holes, okay? Okay. And then I'm going to use a red marker. It's okay. Everything's the same. right? Cool. This is 1K right there, right? This is 10K. This is 100K. Everyone understanding what's going on? And this is for the magnitude response, okay? What about the phase? Remember how I went on my tangent about phase responses yesterday? I think they're very important. So for poles, okay, I'm gonna draw something, okay? Remember how this right here is my pole, right? That's my pole. So this is what you guys are gonna memorize, okay? At the pole, all right, it's an automatic. Let me think. Minus 45 degrees. Okay, phase shift. Everyone understand what's going on? And I'm going to do the following. I'm going to draw a straight line. Okay? Okay, everyone understand what's going on? And I'm going to do this. Okay? And then this slope right here is minus 45 degrees per decade. Everyone understanding how to do a Bode plot now? This is for every pole, okay? So this right here is going to be 90 degrees, okay? And this right here is going to be 0 degrees. All right, everyone understand what's going on? I have a better question. What's this mimicking, or what is this filter mimicking? Right? An RC circuit, where the pole is there, right? Everyone understand what's going on? Is this pretty cool? Anyways, what was I trying to say? So this right here is actually a low pass filter for a resistor. Is that cool, everybody? Low pass filters. So what I'm trying to say is, let me see. You see how if we for a capacitor, right? If the frequency is super low, right? We have 0 degree phase shift, correct? It's an open, right? And we get 1-to-1, right? The output and the input go up and down like this. There's no phase change. Can everyone agree with that? 1-to-1 power, 0 dB, 1-to-1, right? V out equals V in, right? But now, do you see how we start increasing the frequency, right? And you see this impedance? This is why I think the phase response is super important. Is the phase is saying something, we're changing this capacitor from the real domain to the, impedance imaginary domain. So now the capacitor starts acting like a resistor. Full resistance, right? Now you see the full impedance of that resistor. So at this point right here, this is actually very important too. I think, hear me out, I think this is right here, this capacitor is like the best capacitor at this operating frequency if you wanted to use a perfect RC circuit. So if you go like over here, because the magnitude still goes down, okay? Okay? The magnitude's still going down, but for some reason the phase keeps going the same. Are you guys seeing my dilemma? Is that if you go to a gigahertz, right? Yeah, it's going to go all the way down to like 0, right? But for some reason that phase stays at 90. So now I'm introducing you guys, I'm inducing like research into you guys if you guys want to do a master's with me, okay? I think this right here, I think I want to focus my PhD on these points right here. The phase response, there's something going on, okay? So point is, I'm saying everything else is pointless over here. But this right here is money. So this right here is your money range, okay? Anyways, it's okay. But are you seeing what I'm trying to show you guys? RC circuit, this is the answer, okay? That's what this is, experiment 1. Done, okay? So, oh, shoes. You see, I didn't use my secondary paper. Oops, I'm in trouble. I gotta clean this table up. This is why I have 2 pieces of paper. I'm gonna show you guys zeros. Or zeros, yeah. Poles, yeah. Zeros, okay? And I'm gonna draw it like this, okay? For zeros, okay? 1K. right? Everyone's going to memorize this, okay? For zeros, they go up like this. Right here. Everyone understand what's going on? And this right here is 10K, 100K, right? And this right here is 0.1, okay? Is that good with everybody? Everyone understand what's going on? The slope is plus 20 dB per decade, okay? Good with everybody? So what's the value right here? And how about this guy right here? Easy stuff, right? How about the phase? First, draw your line, right? For zeros, okay? You're gonna do this with me, okay? Go to the pole, right? Or to the point, right? Just draw a random dot right there, okay? It's gonna be plus 45 degrees, okay? Draw your straight line. Wait, like that. Draw your line there. Draw your line there. Draw this. Draw that. Right? It's actually a straight line, okay? This is plus 45 degrees per decade. Okay? The slope. So what's the phase over here? Plus 90. And this one here is 0. Plus 0. Alright? What kind of filter did I build here? Is that how I want to show you guys? It's not an inductor. I was gonna say it's an inductor, but inductors look more like this. Actually, 0 dB. That's an inductor right there. Okay, because it's the passive circuit. So hold up. Anyways, I'm blanking out. You know why I call this a 0? Think of like a hole. Like here's like a hole or something like that, and I flip it like this, right? You see that? It's a 0. It's a hole. Okay, I'm a visual learner. Okay, I have to draw these mental pictures. What's that one song everyone hates or memorizes? X is equal to negative v plus or minus the square root of. Yeah. I gotta have these little mental notes. Okay, I'm not a number weird guy. I have to sing the song. Okay. Everyone understand what's going on? So I'm about to do the following, okay? Let me see. Remember that one circuit we just did? V out over V in. Let's see. Let me think. 1 plus F over F3 dB, right? Remember that? And I'm just doing the yeah, I'll just leave it like that. For F3 dB, right? It's gonna be, what do you call it? 1 over 2 pi RC, correct? Let's say R, I'm gonna throw numbers in, okay? It's 1 kilo ohm, all right? And C is equal to 1 microfarad, okay? So what's this equal to? 1K, 1U, right? Kilo and micro cancel out to give you milli, and then milli goes up here, and then it's like signals and systems. Who here likes MATLAB? Who doesn't? I don't know. You don't have to just use MATLAB to do like crazy, I don't know, complex math. You can use it to just check something. So guess what I'm gonna check? Check my problem. Because I can use my phone. Let me just check. Well, I'm getting messages. Anyways. Oh look, polls. Should I run this? Let me run this. For those who didn't show up to my lecture last night. Polls, zeros, right? This is just a homework problem. Kicking our box. Let me see. Let's see if I can run this. Oh, that's a fat 0. See, that's a 0. That's this little Plots transform, okay? And where did I get that S? Like, actually, give me a second. S real H. Where's H coming from? My num, my den. What the heck? Run. Why is it looking like that? Give me a second. Alpha 1, 20. Oh, I know what's going on. 7. There we go. This is a Laplace transform. And then if I flipped it like this, right? Actually, like that right there. Here's the real axis going like this way, right? Here's 0 to 10, 0 to minus 10, right? Right? You see that right there? And then here's the imaginary axis right here like this, right? Right? Everyone seeing that? And these poles are on the left side of that, which means it's stable. Everyone seeing what's going on? Signal systems? Poles, zeros. And if I drew a line like this, you'll get something like this. Let me show you. Frequency response. Cool, right? What if I pull those poles closer to the axis? So where's my frequency? I don't want to play with that. It's okay. I don't want to play too hard. I'm trying to calculate. R is equal to 1,000. C is equal to 1e minus 6 for 1 micron. F 3 dB is equal to 1 divided by 2 times pi times R times C. That's the answer. Control E, enter. 159 hertz. Cool? Everyone understanding what I'm trying to do? What if I do the following? If I wanted a stronger resistor, so 10K, 15K. You guys like that? Or actually, no, that's not 15K. That's 15 hertz. So if I make the resistor strong, I don't want that. Let's make this capacitor stronger. Let's do 7. There we go. There we go. I like that. Okay, so I'm going to do an experiment right now. 1K resistor, right? And 100 nano or 0.1 micro. Okay? And then let me see. Hey, Leo. Okay, so where's my 1K resistor? Yeah, and then my 100 nanofarad. Okay? So we're predicting the circuit, right? So we should see a pole, right? Or we should start seeing a dip at 1.59K, right? Okay. 100 nano.
I kind of gave you the last one. They're over there.
Oh, where is it?
Right here.
Oh, there it is. 100 nano. Did you measure it?
No, I just kind of trusted the pin.
I would measure it if I were you. Okay, so this is what I mean by active lab, okay? Here you go. So I'm going to show you something cool. Let's check chat. Chat. Well, how are we doing? Chat, we doing good? We're doing good. Are you hiring for Twitch mod? What the heck? You guys are funny. Who subbed? Beating?
I give it
10
10 nano.
nano?
Yeah. So I gotta be fine.
Should we do 10 nano? Let's calculate it again. 10 nano is 10 E minus 9. I don't like this. Short, eng. No. Short, format. Wait.
We're good.
Short, eng.
Well, like 87.
There you go.
I guess I was making full contact.
15K. Oh, what?
It's 87.
It's
It
87?
wasn't making full contact.
87 nano?
Yeah.
87 nano?
Yeah.
So 1.82, right? So at 1.82, we should see a pole. Okay? So I'm going to do a cool demonstration for y'all. Okay? So no more writing, okay? Time to do work. Camlink. So this right here is the oscilloscope that's in front. Now we're having some fun, okay? Active lab. Okay, this is what I would have done for everyone. Everyone's gonna build a circuit. Actually, I would have made everyone design their own circuit. Keep it below 100K, maybe? And design me an RC circuit and a high pass and a low pass filter. So I would leave it up to you to use a capacitor in an inductor. Wouldn't that have been a fun experiment? But personally, I only have 2 of these. It would have taken a while, okay? Personally, okay? So I have the circuit right here. You guys like my 4K ultra camera? Wish I did stuff like this. Yeah, funny enough, I use this. This is actually my face cam one. This is my face cam camera. So I have this like cool thing. It's called it's by Elgato, a prompter. So it has like this screen thing that like mirrors, and it's like a 1-way mirror. It's really really cool. Anyways, this right here is my resistor. This is my capacitor. So oh hey Leo, could you get me 2 colored probes, like oscilloscope probes?
Yeah.
And a function generator probe. Thank you. This is my, what do you call it, PSA or whatever they call it. These are oscilloscope probes. Okay? Someone keeps using the function generator clip alligators as oscilloscope probes, and I'm like, don't do that. So, anyways, let me see if I can zoom out. This is my camera. All right. Let me just click on. Okay, thank you. Wish we had different colors.
Yeah.
Do we not have colors in
I
this?
can get you the gray one if you want.
Yeah, can you go give me the gray one? Because I like color coding. I'll bring the color probes in here one day. I just bought a couple new ones. So let me just show you something cool. There you go. My mouse away. So this is my function generator. Okay. And then, oh yeah, I have a dot here. Stab myself. I'm playing, not really. Just the color markers. Okay. Here's my probe 1. Here's my input probe. Okay. And I'm gonna input it right here. Right. This is my my circuit right here. Okay. This is my input. Right. Everyone seeing what I'm doing? And then this right here is my ground. I'll just do it like this. Actually, I'll just do it like that. Yeah, give me a second. There we go. I think it's easier when things are in the board, okay? Is that a better circuit? Okay, here we go. Input, right there. Here's my ground over here, right? Everyone see what's going on? Now I have a gray probe right here, channel 2. Make sure with these probes, please make them, set them to times 10, okay? When you put them to times 10, it introduces a times 10 like fat resistor. So it kills the noise right here, okay? So it's really nice, okay? So just make sure your oscilloscope right here, the settings. Let me see if I can darken this. Can you guys see that? Let me just turn on my filter. Cool, right? Set it to times 10. See that right there? Okay, make sure that's set up, okay? Right. Okay. Anyways. So I'm gonna probe the output right here, okay? Probe right here. Are you guys being treated special? Because I care for you guys, okay? So all the oscilloscopes in here have this thing called an arbitrary function generator, okay? AFG, and it's disabled because I don't think Dr. Greg purchased them originally when we got them. So I bought this for this one right here. So this one works now. So I only have 2 of them. So this acts like a what do you call it? A function generator. Okay. Oh, I want to drop the circuit. Just push it right there. Okay. So now I have my input signal. I have my output signal. Okay. Come on, focus. There you go. I'm gonna focus it right here. Here's my ground. Any questions? Cool. So, let's get back to work. Zoom this guy in. There we go. Turn down the filter. Zoom that in. You guys like that zoom? Let me see. It's too washed. There we go. Is that better? I have a polarizing filter on this one, by the way, so it darkens the room if I want to on this camera. It's super, super cool. I know, I'm a photographer. If you need pictures, let me know. So here's the arbitrary function generator, AFG, right there, right? Let me use a yellow marker, see if this is bright. Hey, it's bright. There you go. See AFG right there? Now it's enabled. If I press on it, like I can set like a function generator, continuous burst, sine waves, look at all this cool stuff. And I think our maximum frequency can be like, and oh look, high Z, 50 ohms, cool stuff. But if I go to measure, let me just delete this. Okay, so measure right here. I have this cool little tab because I paid for it. FRA stands for frequency response analysis. Okay, so my input is channel 1, my output is channel 2. Okay, control loop response Bode plot. Bode. They call it Bode. That's how Dr. Baker called it. Okay. Now I have everything set. Okay. See if I can move this guy. Will it let me move? It will. Nice. Okay. So I'm going to double click on this. And what did we predict the thing to be? 1.5K? 1.8K? So I'm going to go high Z because it's 1K is greater than 50 ohms, right? So I'm going to do from 100 hertz. Yeah, 100 hertz to 100 kilohertz. Kilohertz. Enter. Okay. And then I'm going to do how many points per decade? Let's do 5. Okay, because I want to get this done. Preset presets everything to defaults. It does like a what do you call it? It zeros itself. Okay. And now this red button right here turns on. See this red run stop right here? Okay. If I press it, boom. Now it's acquiring data. You guys like your master class? So what it does is it measures 3 signals for like a period of like 10 periods or 20 periods. It does it 3 times, gets the average magnitude, the average phase, and then it plots it on that table right over here, okay? And guess what? This table, if you have a USB, what do you call it? USB stick, this guy right here. Yeah, this little guy. Cool. You can put it in there, get the CSV.csv, and put it in your MATLABs. And better yet, if you have a microphone and you put this in there and you wanted to record something like an audio sample, you can, and then you can upload that to your MATLAB, build a digital filter, do some cool 480 projects. You see, we EEs can do a lot of cool things, and those CPs, because they have microcontrollers and all this stuff. We have digital signal processing. Okay, we have filter response. We have all these other cool things, amplifiers. Okay, so I want to show you guys that we can do some stuff. And I think a Bode plot is being drawn, but was that it? Did I finish? What the heck?
How much was one of these machines?
Pricey. Let's see, something is wrong. Why am I getting 30 dB? Times 10 times this. Let me do something else. Something's wrong. Let me throw 1 volt. Input output. These are the right probes, okay? Let me just run it again. Okay, preset. Preset again. See, this is what I would do in the labs, okay? Okay, let me see. At low frequencies, we should see 1 to 1. That's not 1 to 1. Something's wrong. Something is wrong. It should be 1 to 1. So channel 2 is multiplied by 10. Is this probe busted? I think this probe is busted. Abort. Hey Leo, go grab me another probe.
Which one?
Get the black one. Something's wrong with this probe. Because let me just do the following. Okay, here you go. Thank you. Something was wrong. I don't like that. Okay. Let me just measure this guy right here. Why is it? That's 1 to 1. And this is 1 to 1. Okay, now it's working. I think something is wrong with that probe or something. That was so weird. Okay, now let's do it again. Reset. We should see 1 to 1, okay? Run. Let's see. Is it 1 to 1? Come on. Where's the blue wire? Unless they're perfectly lined up, yeah. Hey, yeah, I think they are. There we go. Something was wrong. Let me know. Who keeps breaking my probes? Now that's at 0 dB, right? Getting your money's worth? And guess what? We would, this is what we do in real engineering. We just let the test equipment do our work, and then we just go out, go get some pizza, enjoy cooking. It's building the Bode plot right in front of you, right there. Is that cool with everybody? Right? Let's look at it. If I were to, let me see. I don't think I can get rid of that. Can I zoom into this? Okay. Let me zoom. Let me see if I can click down on this. There we go. It won't let me. Yeah, it's okay. Anyways, I'm going to double click on this. I'm going to do not auto scale. I'm going to do, what do you call it? What's my frequency that I care about? Let's do, I like that, it's fine. Double click here. 0 dB. Enter. Y-axis, boom, boom, boom. Wait, oh. Sorry. Minus. Oh. None. Backspace. 80 dB. Negative. Okay, none. Okay. Enter. This right here is 0. Enter. Is that a lot better?
Yeah.
Cool. Now let me just see. See if I can do a cursor measurement. I wonder if I can measure with my cursors. Cursors. Yes. There you go. We're making money. Hey, because we're getting results. And where is our 3 dB? How do I get rid of this screen? It's right there. Okay. Fine. 3 dB. There we go. What's the answer? 1.783 at 3 up minus 3 dB.
What's the phase? Actually, I think the phase is better. If I go to 45 minus 45 degrees, that's an easy number to memorize. Right there. Is that the answer? You guys like that? That's what I would have wanted everyone to do for their experiments. I think this lab would have been super fun to do, but I was like, deal. Here's your cookies. Here's your active lab. I teach you guys what's going on. All right. You guys like this lecture?
Yes.
And then yeah, so that's it. And I could show you another thing, but personally, I think I'm pretty much good. Are there? Actually, do you want me to do another thing?
Sure.
Another circuit?
Sure.
Actually, let's do a high pass filter.
Oh yeah, well that's circle first.
Huh?
Well that's circle.
Yeah. So basically, I'm gonna use the same pole, right? Right? But it should be flipped. Cool. So what I'm gonna do. So at that, we should see the same number. We'll see what's gonna go on. Okay. So I'm gonna grab this output. Okay. And then all I'm gonna do is just take out all the probes. Okay. This was channel 2. So channel 1 is gonna be here. My ground flips. Maybe if I had a universal ground probe. There we go. This right here is my new ground. Give me a second. Okay, this is my input signal. Boom. And here's my probe 2. Okay, there we go. And I'll end it right here, okay? So now let's do the following, okay? So this is what I mean by you can do a lot of cool things in the lab. So let me go from, let's do 1 meg, okay? And let's do 6 points per decade. Reset. Ready, set. Oh. And that's an experiment. Stuff like this, it's pretty fun. This is real engineering stuff. Remember that thing I did with you guys in class with that IV plotter, that curve tracer, that big machine? Cool stuff like that. You just boom, get your answer, go home. This thing too, another engineering tool. Boom, go home. All right, what I'm trying to say is electronics is super cool when you're given the cool tools and makes your job a lot easier. You understand what's going on, and you can take it to your boss and be like, I know what's going on, how to make money, how to build this thing, and get on to your next project. All right, I'm giving you guys these resources and making sure you guys will have fun in the labs. Okay, so let me see. It is a high pass filter. I hope it's filtering. Let's see. Okay, ground. Probe. Probe, yeah. Why is... Okay, the phase is there. That's fine. It doesn't know what to do. It's okay. But we're at 10 kilohertz. What the heck? Is something not connected? Give me a second. Arbitrary function generator? There's no sine waves. What the heck? Oh, are you kidding me? The circuit what? Abort. You want to know what the problem was? Crappy breadboards. Why the heck is that happening? Oh, there we go. You see the numbers now? I want to end it here. Probe. Ready, set. Now we get some numbers, okay? It looks like my Wi-Fi is bad, but it should be okay. You see that sine wave right there? No. It's a pretty bad sine wave. Why is it at 20 darn dB? Why is that 20 dB? It's a high pass filter. It's not working the way I want it to. Now I'm getting sad. Let me just see what happened. Oh, you know why? Wasn't darn probed. Something's wrong. Anyways, it's okay. I'm gonna abort that there. But you guys saw the first experiment, right? Was that pretty cool? Are there any questions about today's lecture? All right, y'all. I'm gonna end it right there. Let me see. Have a good day, everybody. And then I'm gonna do another special lecture after this. It's not a special lecture. It's more like a special topic. Okay. All right. Have a good day.